Swayam Prabha. Digital India. Educated India.
Till now, we have considered a simple rotor system analysis either for transverse vibration or for torsional vibration. The main focus was till now for introducing various kind of terminology in the rotor dynamics and simple concepts and phenomena which occurs in transverse vibration or torsional vibration. And till now our rotor model was simple. In the last class we saw that when we considered 3 degree of freedom rotor model, we had difficulty in handling the big equations. So, we can expect if the degree of freedom is 4 or 5 or more like 50 or 100 in actual practice, we may face difficulty with such methods. So, now onwards we will be having some focus on the tool to be used for analyzing such rotor system. And we know that there are 2 very popular methods which can handle large degree of freedom system in rotors. One is the transfer matrix method and another is the finite element method. Apart from this, there are some other methods also, but these 2 methods are developed mainly so that we can able to develop them in a more programmable form, so that depending upon the complexity we can able to use them without much difficulty. So, today's lecture is in that direction, is on the transfer matrix method, and let us see what are the different concept we will be covering in this particular lecture. So, this is the torsional vibration by transfer matrix method, and we will be analyzing both free and forced vibration with this method. Various concepts regarding this method are like stations, shaft, or disc segment or subsystem. Then the point and field matrices, overall transfer matrix, boundary conditions. So, these will be introduced in the lecture. Coming to the transfer matrix method or TMM method, unlike in the previous case like Newton's method or D'Alembert principle or any other method like Lagrange's equation or Hamilton equation, Hamilton principle. In this particular case, we try to derive the equations of some segment of the rotor system like shaft segment, disc segment or coupling segment, and then once we have these equations for these segments, we can able to use them for any complex system. So, let us see that how we can able to use this method and how we can able to develop this particular method. So, here we have a rotor which is having large number of discs. So, you can able to see here discontinuity is there. So, that means we can able to take any number of discs. So, let us say n number of discs are there. This whole shaft is supported on frictionless support, but as such we will not be having any problem in the boundary conditions, because boundary conditions will come at the end of the problem. So, basically in this particular case we have one shaft. So, this is the shaft segment, free body diagram of the shaft segment, and the disc, this is the free body diagram of the disc. So, using this free body diagram we will try to develop some form of equations, governing equations. The governing equations will involve what are the field variable at various points on these segments. These points in transfer matrix method are called station. So, this could be one station, this could be another station. So, similarly, you can able to see that we can have n number of stations or in a particular system, and we at one particular station the either the this angular displacement of the disk and associated torque. So, at one particular station we will be having two field variable, one is the angular displacement and the torque. So, we will try to relate these two field variable from one end of the shaft to the another end using the free body diagram. Similarly, for the disk we will be trying to derive the field variable relations which is there in the left of the disk side and the right side of the disk, because of the inertia we expect that the torque at two ends of the disks from the shaft reactions will be different. So, we will be having some change in the torque, and these relations which we will be developing will help us in transferring the information from one end of the rotor system to another end. Now, let us take the free body diagram of the disk and try to relate the field variable at either side of the disk, that means left of the disk and the right of the disk, what are the field variables are there, how they are related. So, we have a disk, and from the torque from the shaft we have, let us say, in the left side of the disk we have this particular torque which I am designating as left of, let us say, this particular disk is any representative disk, let us say this disk 2. So, torque in the left of the disk 2 will be representing like this, and direction of this is, when we are looking from the right side, is actually having clockwise direction. So, vectorially we can able to represent this in this direction, negative direction, and the displacement of this particular disk which is phi z, let us say 2, which is having direction in the positive direction. This is the positive convention we have used for this particular angular displacement, and another torque which is coming from the right side of the disk 2, because both end of the disk is connected by shaft, and we have removed from the shaft to obtain this particular free body diagram. So, we have, let us say, the torque which is right of this 2 will represent as T back subscript R, which is representing right side of the disk 2. So, this terminology is we should able to understand carefully, because we will be using this now very frequently. So, the back subscript represent the either left side of the disk or right side of the disk. Always we will be referring with respect to the disk, not with respect to the shaft. So, you can able to see these field variables will be representing with respect to disk, either left side or right side of the disk. So, now you can able to see this particular torque is also having similar positive direction as of the displacement. So, now we can able to relate the field variable which is there in the left side of the disk and in the right side of the disk. Because this disk is a very thin disk, so the displacement, angular displacement at either of the disk we expect will be same. So, we can able to write that the angular displacement of the right of the disk 2 is equal to angular displacement left of the disk 2, because disk is very thin. So, we expect these two angular displacements will be same at either side of the disk. Now, to relate the torque, we can see the free body diagram that we have external torques are right of disk 2 and minus, that is left of disk 2. These are the two external torque, which reactive torque which is coming from the shaft, and that should be equal to the inertia of the disk. So, that is, let us say, polar moment of inertia of the disk is I p 2. So, and angular acceleration of disk 2. So, this is relating the torque and this is relating the displacement, angular displacement. Now, because as such we are considering the free vibration or forced vibration. So, if we are considering, let us say, free vibration, we expect that the whatever the motion is taking place will be having simple harmonic motion. So, that means we will be having, let us say, with frequency as natural frequency, because if we are disturbing the system, we expect that it will be oscillating with the natural frequency of the system. So, if we, so this is the amplitude of the displacement and this is the frequency part, and if we take the double derivative of this, we will get this quantity. Okay. Omega nf is the natural frequency of the system. Now, this we can able to substitute here. So, we can able to write this equation here as, let us say, torque at the right of disk 2 is equal to, I am rearranging the terms, omega square nf I p 2 and phi left of disk 2. This substituted in place of this, I have substituted now this one, and plus torque in the left of disk 2. So, this particular torque I have brought in the right side. So, now this expression I have rewritten here, and we have, so this is one equation and this is second equation. So, you can able to see carefully these two equations are relating basically field variable in the right side and the left side of the disk. This is the displacement and this is the torque. Here also you can see this is the right side torque of the disk 2, and here field variables which are displacement and torque at either of at the left side of this, because in this particular thing we have attached the left one because right and left angular displacements are same. For our convenience, we have added this left here. Now, we can able to combine these two equations 1 and 2 in a matrix form. So, this is displacement and torque. I am writing the subscript and back subscript and the subscript in the outside of the this vector, and we have one matrix and another field variable vector which is belonging to the left of disk 2. So, if we want to enter the first equation, you can able to see that we have 1 0. So, if we expand this first equation, we will get this one. Now, the second equation can be inserted in here, and we will see that this will be omega nf square I p 2 and here 1. So, now we can able to see that we have inserted these two equations in a matrix form, and this particular matrix we can able to write it as, let us say, S is a state vector which is representing the angular displacement and the torque right of this 2, and this particular matrix I am calling this as a point matrix P corresponding to disk 2, because you can able to see the disk 2 mass moment of inertia, polar mass moment of inertia is appearing here. So, that subscript is representing that this point matrix is belonging to disk 2. Now, another one is the field variable that is left of 2. So, you can able to see that this particular relation is relating the field variable which is there at the left of the disk 2 to the right of disk 2. That means, if we know the field variable at left of disk 2, if we pre-multiply by point matrix, we can able to get the field variable in the right of the disk 2. We develop a point matrix which was relating the field variable in the left of the disk to the right of disk. Now, we will take the shaft segment and we will try to develop similar relation of the field variable in the left side of the disk of the shaft and the right side of the shaft. For that, again we will refer to the free body diagram of the shaft. So, shaft is this, and we have, let us say, torque. This is a second shaft, and disk 2 is basically we expect it should have been here. So, and here we expect disk 1. So, this particular torque will be representing with respect to the disk 1. So, I will be writing this as torque right of disk 1, because this particular end of the shaft is attached to the right of the disk 1. So, we will be representing that as torque which is right side of the disk 1. Here we can expect we will be having torque representation as left of disk 2, because this particular end of the shaft is attached to the disk at the left. So, we will be representing this particular torque as left of disk 2. We have torsional stiffness of the shaft, let us say KT2, and now vectorially we can able to represent basically this torque as this one, and this torque, obviously they should be equal and opposite, and we have, apart from this torque, field variables, that means that is the displacement. Here we will be having displacement of disk 1, that is right side, and here we will be having displacement of disk 2 left side. So, our aim here would be to relate the field variable which are here in the left side to the right side, so that we can able to have similar expression as the we had for the disk case. So, let us use these relations. So, you can able to see that we have in this particular case the torques. So, from free body diagram of this, we can able to relate the torques which is left of 2 is equal to torque right of 1, because there is no other torque acting on to the shaft. So, these two torques should be equal in magnitude. And regarding the twist, now whatever the relative twist between the two end of the shaft is taking place. So, I am representing that as, let us say, displacement of left of 2 and angular displacement right of 1. This is the relative twist. If we multiply this by torsional stiffness of the shaft, we expect this should be equal to the torque. So, let us say this is torque, one of the torque, right side of the 1. So, this is relative twist into torque, we will be getting the equal to the torque. Now, we can able to rearrange these equations like this. So, first I am writing this as left of 2, the angular displacement is equal to right of 1 plus basically divided both sides by KT2. So, that I have this expression. So, this is the rearrangement of the second equation. So, we have one equation this and we have another equation this. Now, you can able to see that in this side we have field variable related with the left of this 2, and this side we have displacements which are right of disk 1. So, we can able to combine this in a matrix form like this, as we did for the disk case. So, here I am saying left of 2 is equal to some matrix, and we have field variable, angular displacement and torque for right of 1. So, always, as I told earlier, we refer left and right with respect to disk only. So, you can able to see that if we want to insert this equation first, this is second equation. So, that will give us 0 1. So, if we expand the second equation, we will get this. The first equation can be inserted, and this will give us 1 and 1 by k t, and I am putting the 2 outside of the matrix. So, it is representing this particular matrix is related to the second shaft, and in more compact form we can able to write both the state vector as S left of 2 is equal to, and this matrix I am calling this as field matrix for this 2 for shaft 2, and this is the state vector right of 1. So, F is the field matrix, and earlier we had P matrix, which is point matrix. Okay. So, here you can able to see that we are relating the state vector which is right of disk 1, that means this side, and if we pre-multiply that by field variable of this particular shaft, we will get the field variable and the right side of this particular shaft, but left of disk 2, because disk 2 is here. So, that will be belonging to the left of disk 2. So, now we can able to use this develop transfer matrices, the field variable and point matrices, to obtain the equation of the any rotor system. So, now we will see that how we can able to use this basic equation for development of the whole governing equation of the shaft. So, now consider the shaft 2 and the disk 2. Now, let us see the field variable. Here we had the field variable or state vector which is right of disk 1, and here we had state vector left of disk 2, and field variable here will be having, that is right of disk 2. Earlier we had these relations. I am again rewriting those expressions. So, right of disk 2 we related with point matrix of the disk 2 and state vector left of disk 1, and in the second case we developed state vector left of 2 with the field variable of the shaft 2 and the field variable right of disk 1. So, these relations we earlier obtained. Now, we can able to see that we just I will repeat again this. So, these state vector we related earlier. So, first one was state vector right of 2 we related with point matrix of disk 2 with state vector left of disk 2, and in second case we related the state vector left of 2 with the field matrix of the shaft 2 and the state vector right of 1. These two equations can be combined. We can able to see that this particular state vector can be substituted here. It can be substituted here. So, what we will get? We will get state vector right of 2 is equal to P 2 point matrix for disk 2 into F 2 and state vector right of 1. So, you can able to see that once we substituted this here, we could able to relate the state vector which is right of disk 1 to the right of disk 2 directly. So, that means the state vector which is here and state vector which is here we could able to relate directly, and this particular matrix we can call this as let us say U matrix, which is transferring from right side of the disk 2 to right side of the disk another disk. So, let us say this is U 2 which is product of P and F. This ordering is very important. So, U 2 is the product of P 2 and F 2. If we do the multiplication F 2 to P 2, that will be incorrect. So, we should be careful about the ordering of this, that U 2 is defined here as P 2 into F 2. And we know P matrix and F matrix, and if we multiply this, we can able to obtain the form of the U like this. So, because it will remain 2 by 2 matrix. So, if we multiply P 2 into F 2, we will get K T. I am putting the subscript 2 outside. And last term I P 2 and K T 2. So, in this this we can call this as transfer matrix. Now, you can able to see that this particular transfer matrix contains the stiffness of the shaft, mass moment of inertia of the disc, polar mass moment of inertia of the disc, and the natural frequency. Now, we have developed the transfer matrix for free vibration. So, if there is some external torque, which generally we assume that external torque will be acting at the disc. If external torque is present and we want to analyze the forced vibration also. So, let us see how this point matrix and the field matrix will get changed because of the this external torque. So, if we see the equation of motion which we derived earlier, we had this particular expression for the disc from the disc free body diagram. Okay. And generally when we are considering a disc, we took positive direction of the angular displacement in this direction. So, let us say the external torque T e is acting on to the disc, which is in the positive direction of the this particular displacement. Now, because we had earlier this also in the positive direction and the left side of the torque was negative direction. So, you can able to see that this particular torque will find a place along with the torque at disc 2 in the right side here, and if we transfer that other side, so we will be having this external torque coming here, and we had another relation, that is angular displacement in the right side of the disc 2 and the left side of the disc 2 are same. So, now these two equations, as we combined earlier, can be combined. So, we will be having field variable right of disc 2 is equal to field variable left of disc 2. This particular matrix is for disc 2, and in addition to this, because of the external torque, we will be having another vector, this, because this is the last equation is corresponding to the this torque equation. So, we expect another torque here, which is coming from the external torque, and we will be having here 1 0 1 and minus omega n f I p. So, this was the previous point matrix. Now, because of the external torque, additional vector is coming. The difficulty is because of this is coming that we were earlier able to transfer the state vector from one and to another by just multiplying by the point matrix, but now we need to add this also. So, to make more systematic, we will expand this particular matrix by adding a identity equation, that means 1 is equal to 1 as a third equation. Let us see how we can able to do this. So, we have this and this as field variable, and we want to add a identity equation at the third one, because this will not affect as such our analysis, but this will be convenient in handling the transfer matrix. So, here also we will be having phi z t and 1. So, basically last equation is nothing but 1 is equal to 1. So, that means this. So, you can able to see if we multiply this, the last equation is 1 is equal to 1, and the first equation will have this form, this one, and this equation of the torque equation will modify as I p 1, this is, and then the external torque which was outside, now it is coming inside itself. So, you can able to see that if second equation, if we expand, this one will multiply with this external torque, and we will be getting that here like this. So, this equation can be, we can able to get if we expand the second equation. So, you can see that these equations are belonging to the first equation is this one, second is this one, and third one is this one, and by adding this identity our results are not affecting. But here the advantage is now we can able to write state vector, but different state vector. So, I am calling this as S star modified state vector R. So, this particular state vector is equal to the new point matrix 2, this point matrix. I am calling this as star again, and here we have state vector left of 2, this one. This is also modified. So, I am writing this as a star, S star, P star. They will represent the modified field vector and modified point matrix. So, you can able to see now, as for the free vibration case, we could able to write this particular expression very conveniently instead of writing the external torque outside the point matrix. So, we have seen that we modified the point matrix to include the external torque, so that we can able to do the forced analysis, but we are assuming that there is no external torque acting onto the shaft. So, as such, the field matrix components will not change, because we are not introducing any external torque, but we need to change its form, because point matrix is now 3 by 3 matrix. So, field matrix also we need to change to 3 by 3. So, let us see how we can able to modify this. In the previous case, we had the field variable which was relating the two state vectors at either end of the shaft. So, right of disk 1 to the left of disk 2, and we had this as 1 by k t and 0 1. So, this was the field matrix. Now, we want to add 1 is equal to 1 identity equation in this. So, now let us see how this change the form. So, this is the modified state vector left of disk 1, and this is the modified all our phi z. Right of disk 1. Now, the first two equation from this will be giving equation like this, and identity equation we can able to insert as 1. So, we can able to see that the last equation, if we multiply it, we will get 1 is equal to 1. So, this is now modified state vector left of 1 or left of 2, sorry, this left of 2, because this is left of 2. This is a field matrix for shaft 2. This is also modified field matrix, and state vector right of 1 is also modified. So, I am writing as star. So, you can able to see that this is similar expression as the previous one. Only thing is the size of the field matrix is 3 by 3 to accommodate the torque inside the point matrix, but you can able to see that overall form is similar to the for the free vibration case. So, now we have developed the basic point matrix and field matrix corresponding to the disk and the shaft respectively. Now, we can able to use this for obtaining the natural frequency or force vibration for any rotor system. So, now through one example we will see how these can be used to obtaining the natural frequency. So, now I am taking, let us say, a rotor system which is mounted freely on frictionless bearings, is having several discs, and let us say is having total n number of discs. Various stations we can assign. So, let us say this is 0 station, this is station 1, station 2, station 3, and so on. This is station n, and this is station n plus 1. So, these are the various stations where basically we will try to relate the field variable corresponding to these stations. Now, let us start with the left side. The field variable corresponding to the station 0 is, let us say, S naught, because here there is no disk. So, we are not attaching any left and right of the disk, but we are just saying it is a field variable corresponding to station 0. Here we can have state vector, that is left of disk 1 as well as right of disk 1. Okay. Earlier we have related let us say state vector left of 1 we can able to get using the field matrix of shaft 1. Let us say this is shaft 1, shaft 2 like this. So, if we multiply to the S naught the field matrix, we can able to get the state vector left of disk 1, and the state vector right of disk 1 is related with the point matrix of disk 1 and the state vector left of disk 1. So, these two state vectors are related by point matrix. So, if we want to get the state vector in the right side of the disk, we need to multiply with the state vector in the left side. Now, you can able to see that this equation we can able to write as P1, and this can be substituted here. So, we will get into F1 S naught, and we represent this as a transfer matrix U1 of S naught. So, if we multiply transfer matrix U1, which is multiplication of P1 and F2, ordering is important, again I am stressing. With the state vector at 0 station, we can get the state vector to the right of the disk 1. Now, if we want the state vector right of disk 2, earlier we related with the transfer matrix state vector right of disk 1. This we related earlier while deriving the this field matrix and point matrix. Now, you can able to see that we can able to substitute this here. So, we have U2, U1, S naught. So, if we multiply transfer matrix 1 and 2, again the ordering is important. With S naught, we can able to get the state vector right of disk 2. So, directly we can able to get the state vector right of disk 2 means here. So, now we have related the state vector right of disk 2 with the this one. So, on the same line we can able to say that we can able to relate the state vector right of disk n as un minus 1 like this, u2 u1 s naught. So, that means right of disk n is this one, this is the state vector. So, this state vector we related with the state vector at the far end of the shaft using multiplication of these transfer matrices, and now another shaft segment is left out. So, we want the state vector, let us say at n plus 1. So, this we can able to do it in the next slide. So, state vector n plus 1, because there is no disk here. So, we are not attaching any left and right, is related with the state vector or right of disk 2 with a field matrix, that is n plus 1. So, you can able to see, go back. So, this particular state vector and this are related by a field matrix, this particular shaft which is n plus 1th shaft. So, we need to multiply this, pre-multiply this with field matrix of this shaft to get the field variable of this. Now, you can able to see that we have earlier related this one with the state vector at the 0 station. So, that means if we multiply all these matrices, let us say this is a T matrix. So, we can able to relate the state vector at n plus 1 station with the state vector at the 0 station with this T matrix. This T matrix we call this as overall transfer matrix. The beauty of this matrix is the size remains 2 by 2 matrix for free vibration, and for forced vibration, because we will be using the modified transfer matrices, the size will be 3 by 3. So, the size of the matrices does not change with number of degree of freedom system. This is the advantage of this particular method. So, in the expanded form, if we want to write the above equation is having this form. Let us say T11, T12, T21, T22, because size is 2 by 2. So, after all multiplication, let us say these are the terms. This may be a big equation. So, you can able to see that we are transfer the information of the state vector at 0 station by multiplying by overall transfer matrix to the extreme right side. So, from 0 station to n plus 1 station we can able to get the information, and from other relations we can able to get the intermediate station information. Now, let us see how we can able to obtain the frequency equation from which we can able to get the natural frequency for, let us say, the free boundary condition. So, we derived earlier this particular state vector and we had multiplication of various transfer matrices like this. Now, for free boundary condition, let us say this is 0 station, this is n plus 1 station. Because free, so torque at 0 station will be 0, and at n plus 1 station also it will be 0. So, this is the boundary condition of the free rotor system. So, you can able to see that this term will be 0 and this term will be 0. So, if we expand this equation, we will get field variable at 0 station as T11 phi z and 1 at n plus 1, other term will be 0, and then 0 is equal to second equation T21 phi z naught, and other term will be 0. So, you can able to see that the second equation is homogeneous equation. This is the displacement of the free end, it cannot be 0. So, we need to have this quantity equal to 0, and in fact, this will be function of the natural frequency. So, this is the frequency equation or characteristic equation of the rotor system. From this will be in the form of polynomial, and we can able to solve for simple system using the polynomial solution, or by some root searching technique we can able to find the various natural frequency of this particular equation. The second this particular equation, once we obtain the equation of motion, can be used for obtaining the field variable related to each other, so that we can able to draw the mode shape. So, today we developed the transfer matrix method, and first basic thing was the field matrix and the point matrix development, and we have seen that they are very useful. Once we have the information regarding these two matrices, we can able to develop the system equations, and once we have the system equation, we can able to apply the boundary condition, and from there we can able to get the frequency equation, which can be solved to get the natural frequency of the system. This particular method will be illustrating in the subsequent class through some examples, and then it will be more clear how this particular the technique is very popular in industry for solving the problems. In fact, during the 70s and 80s, this method was more popular than the finite element method, and after 80s the finite element method is more popular because of its inherent diversity and easy to implement the boundary conditions. But still this particular method is having advantage of regarding the size, it remains small. And in this next lecture we will not only consider some example, but also we will try to see how damping in the system, in the torsional system can be incorporated, and how this point matrix and field matrix will modify because of that.